Hi guys, so I'm going to talk you through the Physics Foundation exam you did, and just like you, I've not looked at the mark scheme for this one, which means I'm going to go through it in the same way that you are, and I'm going to show the strategies I use to work out the answers, but also look for clues in the questions, because sometimes when you're doing these exams, it's actually getting quite a lot from properly reading the exam paper, and you do better than you think. And I'm also going to explain some little bits of science along the way as we go to help you out. So my first strategy is always to highlight and underline keywords. Now I know you had 20 on a form, but equally you had the written paper as well that you could use to highlight. So it says electricity can be generated using different energy sources, and then match each way of producing electricity to a statement about an energy resource. Now in this one, just worth sort of keeping an eye on things, it's worth 4 marks. There's 5 boxes, which means it's not just 1 mark per box. So I've got tidal barrages. So tidal barrages, probably one you are less familiar with, but if you imagine kind of a big mouth of the river, and there was sea, because as tides rise, they come in up that estuary. The estuary is the mouth of the river, and then it goes back out again as the tide comes in and out. And as that goes in and out, it causes water to rush past a little mini turbine down here that spins and works. So I've got a solar panel, familiar with that, wind turbine, a nuclear power station, and a wave machine. So the first one produces only a small amount of electricity. I'm not sure on that one, so I'm going to leave that one out for a minute, because I don't know how much electricity each produces. It's built across a river estuary. Well, that's good. That's going to be a tidal barrage. Produces a lot of unwanted noise. That's going to be the wind one. Rough seas are needed. A wave machine sounds like a very much a rough sea. The waste is very dangerous. Nuclear power station, which means the one I was not sure on, I've come back to, and that's a solar panel. Had I gone for that answer earlier and made a mistake, it might have made me get all the rest wrong as well, and I need to get all of them right to get the full 4 marks. Next one says, which one of these methods of producing electricity uses a non-renewable energy resource? So remember, non-renewable means it will run out. We've only got limited amounts of it, so let's have a little look. The tides, they don't run out. Sun definitely doesn't run out. Wind doesn't. Nuclear, not sure. And wave machine, waves don't run out. So in fact, it is nuclear. And nuclear power, although it's uranium and we've got thousands of years worth left of it, it is a resource that we can't replace very easily, so it's a non-renewable resource. The next one says the wind is a renewable energy resource. One of the following statements describes a source of energy that creates a wind. Tick the box next to the correct statement. So which one causes the wind? Is it the earth spinning? Is it the gravity, or is it heat from the sun? Well, it is this one. Well, no, it's not the gravity from the moon, so it's definitely not that one. And so I've got sort of 2 to consider. Well, on this one, I'm going to go with the Earth turning its axis, because that, as it spins, spinning, and all the air around it kind of has to move as well, and it causes it. I'm a little bit hesitant because the heat causes air to rise, and that's why I'm thinking a little bit out loud, but actually this is the one that is the most major effect. Complete the sentence by choosing the correct word from the box. So thermal, kinetic, or sound. A wind turbine transfers something energy to electrostatic energy. That's just another way of saying, kind of like saying electricity essentially, but it's the store of electricity rather than the moving type of electricity. So it's definitely not sound, is it? Wind turbine's not heat, so it has to be kinetic. So it's about that movement energy. So the wind turbine, there's my wind turbine, great animation, as it spins round, that movement turns a turbine that generates electricity, and that's the kinetic energy. This is a wind turbine does not produce electricity all the time. Why not? I think we can all get this. It's not windy all the time. And it's only 1 mark, so I've got 1 statement, so that's fine. Next one says a student investigated the properties of 3 insulating materials, and it's an investigation. So I'm probably looking for the fact they're going to change something, they're going to measure something, and they should be keeping some things the same. So I'm looking out for these things as I read them. And before I leap to the question, because this is a common mistake, I am going to take my time to read every bit of information and highlight it. So when examiners give pictures like this, everything in the picture is important. It's not a random Google search. It is actually there for a reason. So there's a thermometer. There's a metal can. It's got hot water all around it. So I'm starting to visualise what that's like. And then insulation. So the cup or the can's got insulation around it. It says in the investigation different. Okay, so that's the thing they're changing. Insulation materials are used to insulate a metal can filled with hot water. Figure 2 shows how the temperature measured by the thermometer changes over 25 minutes for each of the materials. So although they've used the word change, this is going to be what they are measuring. So it's the temperature that they are measuring. So I'm starting to build up what they've done in this investigation. And then I'm finally, before I go to the questions, let's look at what the general pattern is. So I've got the temperature here, and I've got time going by. So they're getting cooler with time. And then I'm just looking at general trends. We're obviously all going down, but I can see that material C is getting coldest the fastest. Right, so now I know what it's showing, I can start to think about what it means and start to answer the questions. What was the temperature of the room when the student carried out the investigation? How am I meant to know that? So I've got a choice of 20, 38, 53 or 80. So let's look for the clues, because it does seem a bit odd. Here's the only data I've got. Well, 80, it's probably not 80 because that's surely the hot water at the start, isn't it? 53 and 38, where are they? Well, they're just kind of almost like random numbers. There's no real reason why it's these. Oh, hang on, that's where A finishes, and that's where B finishes, and C finishes at 20. So, let's think about this logically. What can B get any colder? Yes. And A could get colder, so I'm looking at the fact that the room must be at 20 degrees because that's the material got as cold as it can. Can't get any colder because the room would start to stop it getting any colder. So it is in fact 20. Now, I've seen these questions like this quite a lot, and they often ask you about what, and it's always going to be the lowest temperature at the end. But you see how perhaps I approach it to think through logically and try and look where these numbers come from. Hopefully, when you start to spot that, it's actually an easier guess. It says material C is the highest thermal conductivity. I'm a biologist, I'm not entirely sure what thermal conductivity is. How's the graph in figure 2 show this? Well, let's see if we can work it out. Figure material C. Okay, well, C has lost the most. So I'm guessing, I know what conductivity means. It means like moving heat, because we heard about stuff conducting, and thermal. Well, that means about heat as well. I guess it's heat or electricity over here. So thermal is heat. So which one moves heat the fastest? So I can see it moves heat the fastest because it's got the largest temperature drop. So I started to break down what the words mean to try and help me a little bit and use the data because it didn't immediately know the answer myself. Another student repeats investigation using equipment shown. And figure 1 shows the first set of equipment used. So that was earlier. So that was what we used earlier on, and this is the new set of equipment. So I can see already that the insulation has changed, and everything else looks similar. Even though the readings on the thermometer, they're usually significant, but they're the same as well. Suggest how using the equipment in figure 3 would have affected the student's results. Well, there's more insulation. Right, I've got 2 points, 2 marks to make. So I'm going to say, first of all, there's more insulation. And because this is suggests, I need to develop my answer. So what? There's more insulation. Think what's going to happen. Less heat is lost. Now I could stop there. There's 2 points. But I'd like to develop it. If less heat is lost, bear in mind every bit of information is useful. The temperature will fall more. Yeah, you could say to me, well, these 2 points are really similar, but they're kind of a little bit different. One's indicating we're losing heat, and one is indicating that we are that the temperature is dropping as well. I've definitely made more than 2 points, or 2 points, so should be good for the mark. The students could have used a temperature probe and a data logger instead of a thermometer. And figure 4 shows the data logger, screen and a thermometer. So again, I'm not entirely convinced what a data logger is, not heard of one before. This is a data logger. Okay, it's digital. And a thermometer, yeah, I've got to work out where that is. So I'd say that that is about 38.6, 7, not sure. Right, complete sentences. Choose the right answer. So compared to the thermometer, the data logger and temperature probe have a resolution that is. So resolution is a term you have to learn, and that's the smallest division something can measure. So imagine I've got a ruler. Okay, well the smallest division I can measure, if this was like 0.1, 0.2. So the smallest division I can measure is 0.1. So which has got the smallest resolution. So this can go up in 0.1s, and really on this one the best I can measure with is the nearest half a degree. So data log's got a higher resolution. So if you hear the word resolution, it means what's the smallest measurement that something can measure, and so we'd say it's got a higher resolution if it can measure smaller values or smaller differences. Compared to the thermometer, the chance of misreading the data logger and temperature probe is lower. How to think about which way around the answer wanted, but it's obviously better to use the data logger. The table gives information about 4 types of insulation that could be used in the walls of the houses. Right, thermal conductivity. So I'm going to look at this and not be entirely sure what this means, although we did work out earlier. So felt wall, well, that is the highest, and then polyurethane foam is the lowest. Now for a little bit stuck, just remember that because we're picking these words out, I do remember that word thermal conductivity from earlier on. Where was it? Oh yeah, material C has the highest thermal conductivity. Let's have another look. And material C fell the most. So I could, even though I'm stuck on what that word means, I can now use exam paper to help me out a little bit. Which type of insulation would be most effective in reducing the rate of cooling in a building? Well, that's where I know that because this has got the opposite of before, it's going to be polyurethane foam. Give a reason for my answer. Well, because it has, I'm using the posh word now, transfers, but you could say lose less heat. Okay, so that's good. So it stops the heat moving from the hot water inside your house to the outside of your house. And that be, and I'm just checking, I've got 2 points, but I've got one for my answer and one for my reason, so that's my 2 marks. Question 3, diagram shows a water wave drawn to scale. Like I've not really seen many water waves like that, but you know, you're looking on the sea and you kind of see, you know, there's your ducks swimming on the sea. So that's what they're looking at. Vertical height in centimetres and the distance in there. What's the wavelength? Well, wavelength, remember, wavelength is peak to peak. And so that peak needs to read this very carefully. So I just look really, don't assume it's on the line, but that's from 4 to 8. So that is 4, and that's going to be units, centimetres. Let's write it down here. What is the amplitude? Well, the amplitude is the intensity or the loudness if it's to do with sound. It needs to be a bit careful. It is from bottom to top. Notice there's a 0 here halfway up. So this wave rises by 3 centimetres. These are tiny waves. 3 centimetres. So amplitude, lots of people make the mistake of saying amplitude is top to bottom. It's not, it's centre to top. Right, 12 waves pass an observer in 4 seconds. What's the frequency of the waves? So frequency is the waves per second. Okay. Now you can work this out in different waves. Different ways. But let's break it down a little bit. So I've got 4 seconds goes by. I've got 12 in 4 seconds. I can write out my number. So in 1 second, I must have 12 divided by 4, which was 3. So the frequency is 3. Now hang on here. Oh, and it says give the unit. I'm always checking that it's 3 marks, and I ask myself what I'm doing. And as a rule, a calculation is worth 2 marks. I'm getting 1 mark for this and 1 mark for this. Although the examiners will give you 2 marks if you get the final answer. And if I was really dumb and said 12 divided by 4 is 4, I would get that bit wrong. But I still pick up a mark for this earlier bit, which is why my workings are so important. But the unit, so the unit is, okay, it's called Hertz. I could write it M4, or it's HZ. So think of that car rental company. So that this is a unit you just got to memorise. Okay, a lorry has an air horn. Not entirely sure what an air horn is. The air horn produces sound waves in the air. Okay, it's a horn that makes noise. Use one word to complete the following sentence. Sound waves cause air particles to or think about how sound travels. As someone shouts, what they're actually causing is kind of sound waves to travel through the air, and what that means is particles are bunching up and smashing against each other and causing them to vibrate. Think about a speaker, you feel it vibrating if you put your head next to it. The air horn produces sound waves at a constant frequency of 420 hertz. That means there are 420 waves per second. That's what it means. The wavelength of the sound is 0.8 meters. Really important that when we work in physics, we use the same units, and meters is our standard unit. We shouldn't use centimeters. Calculate the speed of the waves. Right, so this is a tough one because you need to know your wave speed equation. And so the wave speed equation is wave speed, what's in here, equals the frequency times the wavelength. Now, in maths, so what I need is the speed, that's okay. So I'm just going to do the frequency times the wavelength. Right. So that's one you've got to memorise, and there's so much value in memorising your equations. So I can do 420 times by 0.8. Remember, I'm getting 1 mark just for writing that out. Okay, it would really help if wave speed equals 420 times 0.8. It just makes it really clear to examine what you're doing. Can I do that in my head? Possibly not. So I'm going to grab my calculator. Something 320, 320, I think it's 324. Let me just use my calculator to find out. Not even close, 336. So I should get 336 meters per second. Well, that's quite useful to know actually, because sound travels around about 300 meters per second. So just as a check, I've got an answer that seems sensible. If I'd got it the wrong way round, let's say I do 0.8 by 420. I was having a guess, so that time I'd get, an answer equals 0.001. That's really, really slow. Now, 0.001 meter per second, a centimeter per second. Just ask it, how fast is that? Does that seem how fast sound moves? And if you get an answer that doesn't make any sense, well, maybe swap the numbers or multiply the numbers. If you're really, really stuck, just look at the sense of your answer. It might help you make a better guess. Obviously, the ideal is you remember the equation in the first place. Right, some objects are transparent and some objects are opaque. So transparent means light can pass through it, and opaque means light can't. Which one of the objects is transparent? That's nice and easy, glass vase. The others are all opaque. Complete the sentence, choose on some box. An opaque object does not, okay, so does it, well, it obviously does absorb the light because it can't get through. It doesn't reflect it because these objects are not reflecting light, are they? They're not shiny. So it does not transmit light, that means pass it through. A student investigated how the type of surface affects the amount of infrared radiation the surface absorbs. Now, as a biologist, it took me quite a while to realise that infrared radiation is just another type of light. We can't see it, but some animals can. It kind of looks to them a little bit reddish because it's near the red end of the spectrum. But it's just light, and it behaves just like light, just like the visible light. So although it seems different, it's light that makes you feel warm, but other than that, nothing else is particularly different. It says the metal sheet absorbs infrared radiation, the wax melts and the drawing pins fall off. So let's look at this. See, I've got my heat going out. Okay, it's going to be either, I guess it's going to be reflected or absorbed or transmitted, and then the drawing pin will fall off. That's shiny, that's matte, that black. That should be a bit close, shouldn't it? Okay, right, I've got what's going on. In investigation, there are several variables. Draw one line from each. Right, control. You control things, okay, which means you keep them the same. Dependent. What depends on something else? So, if I'm not sure, what depends on something else? And independent, well, like you want to be as a teenager, you don't want to depend on anything else. So let's just see if we can work these out. The distance from the metal sheets to the infrared container. Or does that depend on anything? Really? So it's either control or independent. The surface colour of the metal sheets, let's have a quick look. Well, they've changed that, haven't they? So the independent is the one that you're changing. and so that's going to go that way. Time taking the drawing pin to fall off, well, that's going to depend on the metal sheet. And obviously the distance from the metal sheets, I'm controlling it, I'm keeping it the same each time. So if you remember which one the dependent is, you can kind of work out the independent because it's the one that's left over. And the control, most people do fairly well on. What's the main hazard in this investigation? Let's have a look. Well, I guess you could poke your eyes out of a drawing pin, but I think that's a pretty rubbish hazard. I think they've actually got a heater. And remember, hazards, what can happen to you? So the heater is possibly not enough on its own. So I'm going to say that heater can cause burns. So I'm being really clear. And it's 1 mark, so that's plenty. Drawing pin attached to the matte black sheet fell off first. What can be concluded from this result? Let's have a look at the picture again, just to be sure. So this one's fallen off quicker. Well, I guess the wax is melting sooner. So I'm going to say, well, more heat transferred. Because matte black, and they've already given me some words I might use, things like absorbs and transmits. So I'm going to say, excuse me, sorry, it's really bad timing. I hope you don't have earphones in. So I've got a choice of absorbs or transmits. Well, it's understandable you might use both words. It is absorbing the heat. You think about black things getting heat, but strictly speaking, the heat's got to get through to the other side to melt the wax. In fact, black objects transmit heat. They don't hang on to it very well at all. Whereas silver shiny reflect it. They certainly don't let it through. So I'm going to go with the word transmits. So it's a bit messy. Okay, so I've really got 2 clear points. More heat transferred because matte black transmits more heat more. Right, infrared and microwaves are 2 types of electromagnetic radiation. Remember, electromagnetic radiation is things like radio waves, microwaves, and so on. Give 1 example of the use of each type of radiation for communication. So one of the mistakes we saw in marking was that people would just give it another use. Well, you might know that remote controls are used for communication. Okay, second one's microwaves. Again, we always think about microwaves being an oven, but it's this word communication that's uber important. So for this one, how to use microwaves, we're using mobile phones. Sorry, all right. Hope you can read the fact that it says mobile phones. Right, some of the properties, that's a feature of infrared and microwaves, are the same. State 2 of these properties. Well, that's quite a hard one. So what do we know about them? Well, one of them is that they are all types of light. Remember I said that infrared earlier on is a type of light. So I'm going to go with features of light that I know, which means they all travel at the same speed. So all travel at the same speed. Same speed. And secondly, what else do I know about light? Well, light comes from stars, doesn't it, and travels through space. So all light waves, whether they are microwaves or infrared, can travel through space. Although space, someone might interpret that as being like my space in my bedroom or something. What's special about space? It's a vacuum, so let's change that to a vacuum. So I'll put a slightly better answer now. So they can travel at the same speed, they can travel through a vacuum. Just so you know, in case you're asked, all light waves travel at 300 million meters per second. It is a number you do need to remember. Don't ignore it. Totally. Right, next one says, the diagram shows horizontal forces acting on a swimmer. Clearly not a swimmer in present times because he's not getting out to any swimming pools. So I've got him going forwards, that's T, and going backwards, that's D. And then look, these arrows much the same size. The swimmer is moving at a constant speed, and force T is 120 newtons. What's the size of force D? And I'm meant to find that out. So when I've got a question like this, and when you've got 1 number, so I can't do any maths with it, it's only worth 1 mark. Maybe there's something blindingly obvious. And usually when you've got this situation, especially in physics, the answer is going to be 0 or something else. Well, force D there is obviously a force slowing him down, or he'd be flying forwards, wouldn't he? And there was also this thing that Newton says that all forces need to be balanced if you're travelling at constant speed. So to be balanced, if the force T is 120 and he's not getting any faster, then force D must be 120 newtons as well. If, for example, he was super streamlined or suddenly changed his shape and the resistance on him, the drag, was 60 newtons, he would start accelerating because the forces are unbalanced, and that's Newton's other law, that you accelerate when the forces are unbalanced. If the current in the sea got stronger and there's a bigger force going against him, and so this one increases to 180 newtons, he would slow down. So there's always that kind of looking out for balanced and unbalanced forces. By increasing force T to 140 newtons, the swimmer accelerates at a higher speed. Okay, we just talked about this. Calculate the size of the initial resultant force acting on the swimmer. Well, that's word hardly, isn't it? So resultant, a bit like a result, so what's left over. Again, I haven't got a lot of numbers to work with, so that should be a bit of a clue, shouldn't it, really? So I've got 140 here, and I've got 120 here. So I guess the sensible thing is 140 take away 120 equals 20 newtons. So my answer is 20 newtons, because resultant is a difference in two locations. Okay, question 8. Diagram shows a worker using constant force of 60 newtons to push a crate across the floor. So he's going to raise back. Right, but there you go, 60 newtons going forwards. The crate moves at a constant speed in a straight line. Select the correct arrow to show the direction of the force acted on the moving crate. So it says select because I give you different options in the exam. Well, clearly the friction must be going backwards, so it's pointing towards it. It's counterbalancing it. State size of the friction force acting on the moving crate. Well, again, I've got no numbers, so I can only really go with the fact it's a constant speed. So this is literally the same as the last question. So it's got to be 60. Give a reason. It's a bit harder. So why is it? Because forces are balanced when an object is moving at a constant speed. Okay, right. Now I've taken out some of the lines there. So I've got the fact I've got constant speed and I've got balance. So I've got 2 points, plus I've got my answer up here. So I've more than made 2 points for that question. It's always worth checking though, isn't it? Calculate the work done by the worker to push the crate 28 metres. Right, work done. That's not stuff you do in lessons. That work done is actually is one of these physics words that actually means energy, or energy transferred, strictly speaking. And it can be a little bit misleading. Which does though mean that the units are always going to be the energy units, going to be joules, right? Well, once again, if I'm totally stuck, let's look at what numbers I've got. I've got distance. So I can make a little note over here to see what I've actually got. What else have I got? And I've got a force, 60. So if I've got a calculator, I need 2 numbers, and I've got a force is 60 newtons. And I've got a distance 28 metres. Now I'm going to show you how I would work out a formula when I'm dead stuck and can't remember it. And I'm going to think about it, right, so it's how much energy it takes to move that box. If the box was heavier, would it take more or less energy? Just think that through in your head. If the box is heavier, does it take more or less energy? Well, it's going to take more energy if that box, or there's more, it's heavy and he's going to have to push it harder, isn't he? If he pushes it further, it's going to take more or less energy. Well, clearly that's going to take more as well. So they both go up. So what I need to do then is multiply these numbers together. So I'll do 60 times 28, because that's the way to make both of those have an effect where it makes the final answer bigger. So it's kind of working out logically in my head. So it becomes 60 times 28, which I could do in my head if I wasn't trying to rush. And was 1,680. And I'm going to put the units in as well. So I'm now going to get, now I probably should have written this out a bit in detail. So I could have said work done equals 60 times 28, or it also equals force times distance. which equals 1,680. And I put the answer first. There's nothing wrong with going back and putting down the workings I've just done, because if I've made a mistake, and I see it all the times, somebody's just had a little moment, okay, the answer is 1,680, and they write down 1,860. If you just put this, you're getting 0. If I put this and then this, I get 1 mark, and I've got my units, so I'm only dropping 1 mark. The damage isn't quite so bad. So please, please, please include your workings. A high-speed train accelerates at a constant rate in a straight line. So it's accelerating. The velocity of the train increases from 30 to 42 meters per second in 60 seconds. Calculate the change in velocity of the train. Well, that's just surely, okay, 42 seconds. Seems a bit easy, but let's write it out. So 12 meters per second. Okay. Right. Sometimes these questions will build you up and almost get you each element of an answer before they make you leap in there. So use the equation in the box to calculate the acceleration of the train. Change in velocity, I've just done that. Well, let's say I was dead stuck, and let's say I put 20 because I didn't have a clue. But as long as you use the same number, okay, you're still going to get the mark. Time taken for the change, so let's have a look through. I identified that as 60. Okay, so that would give me, and that one, 0.3. Well, remember that is wrong because that's the wrong number. So I really should have had the correct number. Is 12 over 60, which is 0.2. But what I'm trying to show you is that as long as you carry the answer forwards, or worse, you were dead stuck and you did not have a clue, but you've got this formula, you could have gone, well, I'll stick a 1 there, and I'll stick a 1 there and put 1 over 60 and come up with an answer. So you can make that bit up to carry it forwards. It's okay. So 12 over 60 equals 0.2. What's the units? Well, units are actually a hidden formula. So this unit means meters divided by seconds, or distance divided by time. This unit means newtons times by meters. This one means newtons divided by kilograms. So did I have that? And this one means meters, it's a little bit of an awkward one, divided by seconds, or another way to write it is meters per second divided by seconds. So that's what these units mean. Let's look at how we can work it out if we've forgotten. Well, I change in velocity. So velocity is speed, so that's meters per second. And I divided it by the time. So although we change it, that is the same as saying meters per second or meters per second squared. It's certainly not any of the others, and it's definitely not the 2 newtons, because it's not even mentioned in the question. So remember, units are a hidden way of finding formulae. If I want to look at speed up here, I could just do meters divided by time, or distance divided by time. That gives me the speed. So look out for those. So the answer was meters per second squared. And we had 0.2, didn't we? Right. Last question. Which one of the graphs, A, B or C, shows how the velocity of the train changes as it accelerates? Okay, there's 2 types of graph, distance time graphs and velocity time graphs. I need to just be careful and think through what each means before leaping in with an obvious wrong answer. Right, the velocity in this one is not changing as time goes by. So that means, let's put some numbers on this, 1, 2, 3, is velocity is 2 meters per second constantly. It's not static. That's a mistake people make. That'd be a distance time graph. So it's not this one. This one, velocity over time. Well, if I was to put 1, 2, 3, I can see it's 2 at the start and it's 3 at the end. So that one is getting quicker. And this one, well, it's kind of the same, isn't it? If I put in some numbers in again, it's 2 here, it's 3 here. So I'm down to these 2. So maybe this isn't such an easy question, despite being multiple choice. Let's look for some more clues. Let's go back. High-speed train accelerates at a constant rate. So that should be a clue right down there. So this one is not accelerating at a constant rate. It's getting quicker and quicker and quicker. In the last few seconds, it accelerates rapidly and it's slower at the start. So it is, in fact, B. But notice how I've gone back to look for more clues. Right, what we're going to do now is the 10-mark challenge, guys, and just think about 2 or 3 of the strategies I've used and write those down on your 10-mark challenge sheet, and then you can start to look at how you might develop some of your knowledge as well as some of your math skills and the practical skills from this exam paper. Well done, guys. Thank you for listening.